For any electrical engineering student, when you first start out, there are two fundamental laws that you learn that govern how you interact with, how you think of, and how you solve circuits. They are Kirchhoff's voltage law and Kirchhoff's current law. Now, what Kirchhoff's voltage law states that the sum of voltages in a closed loop will always add up to zero, or the sum of voltage changes in a closed loop, better stated. So here, we gain some voltage from our voltage source, we lose some from our resistor, we lose some from our resistor again, and that means if we add this, subtract this, we should end up back where we are and end up with a total change of 0 volts. And if you think of voltage as height, this intuitively makes sense, right? If you start at a height position, you have some potential energy, and then you walk in a circle, and you end up back where you are. Well, you've just ended back where you are at the same height. The sum of the changes is now 0. Kirchhoff's current law states that for any current into a node, or what that means is a wire, that has to equal the current that leaves the node. This also intuitively makes sense and is based off the conservation of charge. Charges are particles, electrons. They cannot be destroyed, so they have to be conserved. So you have some entering, you have to have some leaving. So that means that that IN has to equal I1 plus I2. But as it turns out, despite this making intuitive sense, that this law doesn't always hold. In fact, there are some certain cases where both of these laws break. And we can see where these are based on Maxwell's laws. Maxwell's laws are where, in part, these Kirchhoff's laws are derived from. So it's in some part taken and simplified. And what Maxwell's laws tell us are that they inform us about the divergence and the curl of the magnetic flux density, the electric flux density, and the magnetic field intensity and the electric field intensity. So fundamentally, Maxwell's laws just inform us about the divergence and curl of the electric and magnetic field. And there are 4 of these laws. This first one is called Gauss's law for magnetism, because it deals with the magnetic field. The second, Gauss's law for electricity, because it deals with the electric field. Then we have Ampere's, and we have Faraday's law. And these 4 laws together make up Maxwell's laws. But before we can really dive in and understand Maxwell's laws and how they can sort of break our Kirchhoff's laws, we have to understand some of these components that make up the laws. What is that funky shape that's the upside down triangle? Well, that's an operator called del. And an operator is something like plus, minus, divide, derivative, something like that. Now, what does del do? What is its operation? Well, the del operator takes the spatial derivative of a vector. It tells you how a vector field is changing. So if I take del of a vector field B, that is a new vector field that describes the rate of change of B. It tells you where B is most changing. And what makes it more interesting in our use case is when you combine it with the other operators, the cross product and the dot product. So del cross B and del dot B. Where this quantity here, I like to think of the cross product as the amount of vector 2 perpendicular to vector 1. So it would be the amount of B that is perpendicular to the direction B is changing. Same thing the other way, except I think of the dot product as the amount going in the same direction. So the amount of B going in the same direction as B is changing. With those two quantities, the cross product of B, this being referred to as the curl, and the dot product of B being referred to as the divergence. So if we were going to take the del of this vector field up here, we may get vector pointing upwards, because as we move up, our vectors are changing to point further upwards. Now, at this point, you may be having the same question I did when I first saw this. Well, del is an operator, and we're doing an operator B. Can't very well do, plus divide 7 and have that work out. Well, that's because, as we looked at before, B's fundamental form just looks like a vector, and so we can treat it as such. So when we're doing that, we're taking the cross product, we're imagining this is a vector, and we just take the cross product normally. Now, what actually is this curl and divergence? Well, you can think of curl as rotational kinematics. So, when I tell you that this is the amount of B going perpendicular to the rate of change, if you remember from your physics class, this is the definition of rotational motion, right? Your acceleration, the derivative of velocity, will always be perpendicular, and that's what results in a circular or curling motion. Similarly, for divergence, if your ball is getting faster in the direction it's already moving, you can consider that to be diverging away from its current position. And that's how I like to think of those two. And then we have Stokes and divergence theorem. These two tell us information about if we know what the curl of A is. If we know the curl of A here equals some quantity B, well then we can get that the closed line integral of A. So closed line integral means any closed line that encloses a surface. So here we have a surface. So if the closed line integral of a along this line equals the surface integral of that quantity b along this surface. So how much of b is going through that surface enclosed by a. Similarly, the divergence theorem tells us that if the divergence of a equals some quantity b, then we can know that for an arbitrary closed surface, so an arbitrary closed surface can be any surface that encloses a volume. So in this case, we can use a square. So the surface integral of a across the surface equals the volume integral of b inside the volume enclosed by the surface. And these two are fundamental for working with Maxwell's equations. And then the final piece of the puzzle to understand the whole thing is flux, which is understanding what those variables were that we're taking the cross product or the derivative of. Right? So how flux and flux density are related to the field intensity was the one of the things I found most confusing about this. It's that the flux density is almost like the electric field intensity after you account for the material, right? So after you multiply, after you add in your permeativity constant here, then you get your flux density, which is the permeativity of the material. So it's just another vector field scaled by some quantity to represent the material the intensity has to be in. And then the flux is a scalar quantity that represents the amount of flux density that passes through the surface of an object. So if we have a bunch of flux going through the surface of this object, then we may say it has a high flux. And that's what flux is. And that's how it relates to the field intensity. And now we have Gauss's law for electricity. This is the first of Gauss's laws. Now, what Gauss's law for electricity tells us is about the divergence here of D. D in this case is our electric flux density. So it tells us that the divergence of the electric flux density is equal to the charge density, right? The volume charge density. So then this becomes useful once we apply the divergence theorem. Because what is the volume integral of the charge density in a volume? Well, it's just the charge enclosed. And this is how we learn that the amount of electric flux density going through a arbitrary surface is equal to the charge enclosed within that surface. Right? Now, this made sense for me until I wondered, well, what happens if we have a charge? What if I wanted to prove this wrong, right? What if I have a charge outside of our closed sphere? Well, now it enters the sphere, changing the amount of flux traveling through the surface, the amount of flux density traveling through the surface, without changing the charge enclosed within that surface. How does this get balanced out? Well, in this case, it's because the field line at some point has to exit our closed surface, and at that point, the contributions cancel out. And then we have Ampere's law. Ampere's law tells us that the curl of the magnetic field intensity is equal to the J, which is the current density, plus the rate of change of the electric flux density. So after we apply our Stokes law to this, what we get is that the amount of H across a closed line integral equals the amount of current density through the surface bounded by that integral here, plus the amount of changing electric flux density through that same surface. And now to understand how this law here may impact our Kirchhoff's laws, we can draw a little diagram here. Let's see. So, here, we can imagine that we have some circuit here, like this. Voltage source, one end connected to ground, and the other to a metal plate. Now, if I asked you in this situation, would you have a flowing charge here according to Kirchhoff's current law? You would obviously say, no. There's no way, right? You have current entering, but there's no way for that current to leave. Now, what if I changed it a little? Say I forgot to mention that there is another metal plate really close to that first one that's also connected to ground. Well, now, obviously, yeah, this is a capacitor. Charge can flow across a capacitor while the capacitor is still charging and it doesn't act like a open. But does any charge go across the capacitor? Is there a hidden wire here? No, as it turns out. No charge goes between the walls of the capacitor. So, does Kirchhoff's current law break? Is it gone? Well, it turns out that if we look at our equation over there, that tells us that the closed line integral here equals the surface integral J plus del T d. Just pretend there's a ds right there. Well, what is this term? This term is the current due to the movement of charges, right? Due to the drifting of charges, hence why it's called drift current. But what is this second term here? Well, we can see how this second term here has the same units as charge as our current may actually solve our little issue here with Kirchhoff's current law. As current flows through the circuit, we get positive charge on this plate. If you remember from your whatever class you've taken, and a negative charge on this plate. And as current flows, more and more charges start to build up. And as that happens, a field is created between these two plates. An electric field that grows as current is put in, so as a positive rate of change. And wouldn't it be great for fixing this if this component here at this part would exactly equal this I drift component over here? Well, as it turns out, that is exactly what happens. This component exactly equals the current coming in, the surface integral of the amount of changing electric flux through this surface exactly equals the amount of current coming into the surface. Right? So, what if we said, well, even though this isn't actually due to the movement of charges, why don't we consider this part current as well? And the name for that is displacement current. Yeah, trailing along the board. But the way I like to remember this is the drift current is due to the drift of charges moving across the wire, and the displacement current is because there's a derivative in this place. Yeah, forget about the mint. But that's how I like to remember it. And that's what allows us to solve our problem of conserving Kirchhoff's current law. In this case, by considering this second component here equal to also to be current, or saying that the current isn't actually, when we say we want to conserve current, we're not conserving the movement of charges, but we're conserving the line integral of the magnetic field, which can be due to charges or can be due to the changing electric field. Okay. Right, and now we can move on to our next law, which is markedly simpler, which is Gauss's law for magnetism. What Gauss's law for magnetism tells us is that the divergence of the magnetic field is equal to 0. The divergence of the magnetic field is equal to 0. And if we apply our divergence theorem to this, we get that the amount of magnetic field going through a closed surface, the total amount going through a closed surface, is equal to 0. And the way I like to visualize this, so we're going back over to the whiteboard here, is that this fundamentally makes sense. Because if we're given that del dot H equals 0, that means a magnetic field can only curl or can only be circular, hence why there is only monopoles. There's only dipoles of magnets. There's no monopoles. So if we take that presumption and we build our closed surface here, a square, and we want to break this part, that the total amount of magnetic field going through a surface is going to be something other than 0. Well, to have some magnetic field go into the surface, you have to start outside and enter into our surface. And then as we cross through this point, this changes. But since we know from this that it can only be circular, so at some point we're going to have to return to this point to close our circle. That means we're going to have to exit, canceling out the contribution. Same if you start inside. As it turns out, there's no way for you to draw this line, so that doesn't happen. And that's why this gives you this. Mm-hmm. And now we have Faraday's law, which tells us about the curl of the electric field, and specifically that it's the negative of the rate of change of the magnetic flux density. And if we apply our laws to this here, we get that the closed line integral of the electric field equals the negative of the surface integral of B. So if we have some line here, this is our line integral for E. This value is going to be equal to the negative of the surface integral of the amount of changing B through this closed surface. Or not this closed surface, this surface enclosed by our closed line. Now, to understand why this might might impact Kirchhoff's voltage law, we need to look at what Kirchhoff's voltage law actually says. Well, what is voltage fundamentally? Well, really, it's just the line integral between 2 points of the electric field. So when you're taking the voltage of a capacitor, you're taking the line integral between these 2 points of the electric field. And that gives you the voltage across the resistor. Now, what does Kirchhoff's voltage law state? It states that the voltage through any closed loop must be equal to 0. Well, if we write that out, knowing our E, what we get is this, which doesn't match up. This only holds if we are not in a changing magnetic field. And this is actually the driving force behind turning mechanical energy into electrical energy. We can take a magnet, move it through a loop of circuit, and as that magnetic field changes, it incurs a current, which if we have a resistor, or it incurs a voltage, which we then can use to create a current with the resistor, and then charge batteries or provide power. That's how we turn mechanical energy into electrical energy. And it's why this voltage law here doesn't always hold. And then we have our conclusion. How can we rewrite these laws now based on what we learned? Well, the current law before may have said something like the sum of the drift in equals the sum of the drift out, where the drift is the current due to the movement of charges. Now, with our new knowledge, we can say that it isn't just the drift we have to worry about, it's also the displacement we have to worry about. So our drift in plus our displacement current in has to equal our drift out plus our displacement current out. Similarly for voltage, before we may have said that the closed electric field across a closed line is equal to 0, or that the total voltage, the sum of the change in voltage in a closed loop equals 0. Now we know that it isn't 0. Instead, what we should say it's equal to the negative of the surface integral of the changing magnetic flux density through that surface, the surface enclosed by whatever circuit you have. In this case, this rectangular shape here. And that's all. I hope this was interesting and at least somewhat helpful. I learned a decent chunk trying to make this. It took surprisingly long for how roughshod it is. So, yeah, feel free. If I made any inaccurate statements or said anything wrong, feel free to leave a comment or something. Otherwise, thanks you for listening, and peace.